Welcome to this problem walkthrough. In this session, we will explore problem number 2033, minimum operations to make a uni-value grid. The challenge is to transform a 2D grid into a grid where all elements are equal using the minimum number of operations. We'll break down the problem, discuss the approach, and cover the key insights you need to solve it. Let's dive in. In this problem, you are given a 2D grid of integers with dimensions mxn, and a value x that represents the step size for operations. Your goal is to determine the minimum number of operations required to make all elements in the grid equal. During an operation, you can either add or subtract the value x from any element in the grid. If it's not possible to make all the elements of the grid equal, you should return -1. For the input format, the grid is represented as a 2D integer array, and x is specified as an integer. The output should be a single integer, either the minimum number of operations required or -1 if it's not feasible to achieve the goal. Let's look at the first example. The input grid is 2, 4, 6, 8, and x is 2. To make all elements of the grid equal, the differences between all pairs of numbers in the grid must be divisible by x. In this case, that condition is satisfied because the differences, such as 4, 2, 6, 4, and so on, are all divisible by 2. The median value of this grid is 6, and we aim to transform the entire grid so that every element becomes 6. To do this, we perform the following operations: add 4 to 2, add 2 to 4, and subtract 2 from 8. These actions require a total of 4 steps, so the output for this example is 4. In the second example, the input grid is 1, 5, 2, 3, and x is 1. Here, we find that it is impossible to make all elements equal. For instance, the difference between 5 and 1 is 4, which is not divisible by x equals 1. This violates the condition required to make all grid values equal using the given operation. As a result, the output for this case is -1, indicating that it is not feasible to achieve the goal. For the third example, the grid is 1, 2, 3, 4, and x is 1. Here, the differences between all pairs are divisible by x, so it is possible to make all elements equal. The median value for this grid is 2, and the goal is to transform the grid into 2, 2, 2, 2. To achieve this, we add 1 to 1 in one step, subtract 1 from 3 in another step, and subtract 2 from 4 in 2 steps. This results in a total of 4 operations, so the output is 4. The constraints for the problem ensure that the dimensions of the grid and the values within it are manageable for computation, and edge cases such as single-element grids or grids with already equal values should be carefully considered in your solution. To solve this problem, we need to transform a 2D grid into a uni-value grid where all elements are equal, using the minimum number of operations. Each operation allows us to add or subtract a given value, x, from any grid element. A key constraint here is that the difference between any two grid elements must be a multiple of x for the transformation to be possible. Our task is to determine the optimal target value to which all grid elements will converge, minimizing the total operations required. This lays the foundation for the approaches we'll discuss next. One approach we might consider is a brute force method. The intuition here is to try all possible target values between the minimum and maximum elements of the grid and calculate the total operations needed for each. Specifically, we iterate through all values in this range, check if all elements can be transformed to the candidate target value by ensuring their differences are divisible by x, and compute the total operations for valid targets. Finally, we return the minimum operations. However, this approach has significant drawbacks. Its time complexity is proportional to the range of grid values divided by x, multiplied by the grid size. This makes it inefficient for large grids or when the range of values is vast. Additionally, it wastes time on invalid targets, making it impractical for real-world scenarios. To overcome the inefficiencies of the brute force method, we turn to an optimized approach using the median. The key insight here is that transforming all elements to the median minimizes the total number of absolute differences, which directly translates to fewer operations. To implement this, we first flatten the 2D grid into a 1D array. Then, we check if all elements are transformable by verifying that the differences between elements are divisible by x. If not, the transformation is impossible, and we return -1. Otherwise, we sort the array, find the median, and calculate the total operations required to bring all elements to this median value. This approach leverages the mathematical properties of the median, making it both efficient and elegant. The optimized median approach has a time complexity of O, R*C** log, R*C, where R and C are the dimensions of the grid. This is primarily due to the sorting step on the flattened grid. In terms of space, it requires O, R*C, to store the flattened array. The approach is highly advantageous, especially for large grids, as it avoids the brute force method's excessive computations. The median is particularly effective because it minimizes the sum of absolute deviations in a sorted array, ensuring the least total operations. This mathematical property is the cornerstone of this approach, allowing for an efficient solution without exhaustive exploration of all targets. Ultimately, the optimized median approach is the chosen strategy for this problem because it strikes a balance between efficiency and scalability. By relying on well-established mathematical properties, it avoids unnecessary computations and handles large inputs gracefully. While the brute force approach is easier to conceptualize, its inefficiencies make it unsuitable for real-world applications with larger grids or value ranges. The primary trade-off of the median approach is the sorting step, but this is greatly outweighed by the reduced computational overhead. Additionally, pre-processing steps like flattening and transformability checks are minimal in comparison. Overall, this strategy offers clarity, speed, and practicality, making it the best choice for solving this problem efficiently. To solve this problem, we need to transform a given 2D grid into a Uni-Value grid using the minimum number of operations. Each operation allows us to add or subtract a fixed number, x, to any grid element. The key challenge is determining how to align all grid elements to the same value with the least effort. The first step in our approach is to simplify the grid structure. By flattening the 2D grid into a 1D list, we eliminate the need to worry about the positions of the elements and can focus entirely on their values. For example, if the grid is 2, 4, 6, 8, the flattened list becomes 2, 4, 6, 8. This transformation helps streamline the subsequent operations, making the problem easier to manage computationally. Once the grid is flattened, we need to check if it's even possible to make all elements equal. This feasibility check revolves around modular arithmetic. For the transformation to work, all elements in the grid must have the same remainder when divided by x. If this condition is not met, it's impossible to align the values, and we can terminate early. For example, if x equals 2, all elements must either be even or odd. This works because adding or subtracting x doesn't change the remainder of a number modulo x. If the grid is feasible, the next step is to sort the flattened list. Sorting helps us identify the central value, or median, which plays a key role in minimizing the total number of operations. For the example, 2, 4, 6, 8, sorting doesn't change the list, but it ensures we can easily locate the median value. After sorting the list, the next step is to identify the median value. The median is critical because it minimizes the total sum of absolute differences. This is a well-established result in mathematics. Aligning all values to the median requires the fewest adjustments. For instance, in the sorted list, 2, 4, 6, 8, the median is 6 if divisibility by x allows it. With the median identified, we calculate the total number of operations required to align all elements. For each value in the list, the number of operations is determined by abs, element median, /x. Summing these values gives the total operations needed. For x equals 2 and median 6, the operations 4, 2, 4, 6, 8 are 2, 1, 0, 1, resulting in a total of 4 operations. Finally, this accumulated total is returned as the solution. There are a few critical insights to take away from this algorithm. First, the divisibility check is essential. Without all elements sharing the same modulo x, it's impossible to align them. This ensures that the problem is even solvable. Second, the median is the optimal choice for minimizing total operations. This is because the median minimizes the sum of absolute differences, making it the best target value. Additionally, sorting the grid values simplifies the process of finding the median and calculating the required operations. From a data structure's perspective, we use a 1D array to store the flattened grid values, which makes calculations and sorting straightforward. Sorting itself is efficient, with a time complexity of O, m*n*log, m*n, where m and n are the dimensions of the grid. Now, let's analyze the algorithm's complexity. For time complexity, flattening the grid takes O, m*n, as we simply iterate through all elements. Checking divisibility also requires O, m*n, for the same reason. Sorting the 1D array is the most expensive step, with a complexity of O, m*n*log, m*n. Finally, calculating the operations involves another O, m*n, as we iterate through the list to compute the transformations. Combining these steps, the overall time complexity is O, m*n*log, m*n. For space complexity, we need O, m*n, to store the flattened grid as a 1D array, which is the only additional space required beyond the input grid itself. This makes the algorithm efficient in both time and space, given the constraints. To ensure the solution is robust, we must consider a few edge cases. First, if the grid elements don't share the same remainder modulo x, it's impossible to align them, and we should immediately return -1. For a single element grid, no operations are needed, since it's already uni-valued, so we return 0. Similarly, if all elements in the grid are already equal, the result is also 0 because no transformations are required. Lastly, for large grids, the algorithm remains efficient due to its reliance on sorting and modular arithmetic, which scale well. By addressing these edge cases, we ensure that the algorithm handles all possible scenarios effectively and performs reliably under various constraints. The provided solution addresses LeetCode problem number 2033 by minimizing the operations required to transform a grid into a uni-value grid, where each element can be increment or decrement by a fixed value x in each operation. Let's break down the implementation step by step. 1. Flatten the grid. The grid is a 2D list, so we first flatten it into a 1D list using itertools.chain.from_iterable. This makes it easier to process all elements linearly. 2. Sort the flattened list. Sorting the flattened list helps in identifying the median element, which minimizes the total absolute deviations, a key insight for this problem. 3. Check divisibility. For the transformation to be possible, every difference, number flat, 0, must be divisible by x. If any element fails this condition, we immediately return -1, as it is impossible to make all elements equal. For find the median of a sorted list minimizes the sum of absolute differences. Here, it is used as the target value for the transformation. 5. Calculate operations. For each element in the flattened list, we compute the number of x-sized steps needed to reach the median. This is given by abs, number median, /x. Summing these values gives the total number of operations required. 6. Return the result. Finally, the function returns the computed number of operations. If the transformation was impossible, -1 would have already been returned. This approach is efficient, with a time complexity dominated by the sorting step, which is O, n log n, where n is the total number of elements in the grid. Here, we begin by importing the necessary utilities and defining our solution class. The method min_operations takes in a 2D grid and a step size x as its parameters. The first step is to flatten the 2D grid into a 1D list. This is achieved by iterating over each row of the grid and adding each individual element to a new list called flatlist. Once the grid is flattened, we sort the flatlist to prepare for the next steps. Sorting is crucial because it allows us to efficiently find the median and ensures that we can process the elements in a structured manner. After sorting, we check whether all elements in the list satisfy the divisibility condition. Specifically, the difference between each element and the smallest element, base, must be divisible by x. If any value fails this condition, we know it's impossible to transform the grid into a uni-value grid, so we return -1 immediately. This check is essential to determine whether the problem has a valid solution before proceeding further. Finally, we calculate the median of the sorted list, which represents the target value that minimizes operations when transforming the grid values. Once we have the median, we calculate the minimum number of operations needed to make all elements in the grid equal to this median. We initialize a variable operations to 0 and iterate through each value in the flattened list. For each value, we compute the number of operations required by calculating the absolute difference between the current value and the median, dividing it by x. This division ensures that we account for the step size, as each operation modifies a value by increments of x. The result is accumulated into the operations variable. After iterating through all the values, the total operations represents the minimum transformations needed. Finally, we return this value, providing the solution to the problem. This method efficiently combines mathematical reasoning and computational steps to solve the problem within the given constraints. Here, we're working with a simple grid example where the input grid is 2, 4, 6, 8, and x is 2. The first step is to flatten the grid, converting the 2D array into a 1D list for easier processing. When we flatten the grid, we combine all rows into a single list, resulting in 2, 4, 6, 8. Next, we sort this flattened list to make it easier to determine the median later. In this case, the list is already sorted as 2, 4, 6, 8. Then, we verify if all numbers in the list can be aligned using steps of size x. This is done by checking that the difference between each number and the first number in the list is divisible by x. For this grid, every number satisfies the condition 2 to 2, %2 is equal to 0, 4 to 2, %2 is equal to 0, 6 to 2, %2 is equal to 0, and 8 to 2, %2 is equal to 0. Since all checks pass, we can proceed to the next steps. Since all numbers in the flattened list are divisible by x, we can move forward. The next step is to find the median of the list, as the median minimizes the total distance when aligning all values. With the flattened list 2, 4, 6, 8, the median is found at the middle index. Here, the median is flat, 2, which is 6. Once we have the median, we calculate the total operations required to align all values to this median using steps of size x. The formula involves summing up the absolute differences between each number and the median, divided by x. For this example, the operations are calculated as follows: abs 2 to 6 // 2 plus abs 4 to 6 // 2 plus abs 6 to 6 // 2 plus abs 8 to 6 // 2, which simplifies to 2 plus 1 plus 0 plus 1, resulting in a total of 4 operations. Therefore, the output for this example is 4. Now let's look at a second example where the input grid is 1, 5, 7, 10, and x is 3. First, we flatten the grid into a 1D list, resulting in 1, 5, 7, 10. Next, we sort the list, though here it's already in sorted order as 1, 5, 7, 10. Then, we check whether each number in the list satisfies the divisibility condition using x. This means verifying that number flat 0, %x equals 0 for all numbers. For the first number, 1 to 1, %3 is equal to 0, which is fine. However, for the second number, 5 to 1, %3 is equal to 1, which is not divisible by 3. Since one of the numbers in the list fails the divisibility check, it's impossible to align all values to a single number using steps of size x. As a result, the output for this example is -1, indicating that alignment is not possible. In this larger grid example, the input is 3, 7, 11, 15, 19, 23, and x is 4. The first step is to flatten the grid, which combines all rows into a single list. This gives us 3, 7, 11, 15, 19, 23. Next, we sort the flattened list, and in this case, it's already sorted as 3, 7, 11, 15, 19, 23. Then, we check whether the divisibility condition is satisfied for each number in the list. This involves verifying that number flat 0, %x equals 0 for all numbers. For this example, every number satisfies the condition 3 to 3, %4 is equal to 0, 7 to 3, %4 is equal to 0, 11 to 3, %4 is equal to 0, 15 to 3, %4 is equal to 0, 19 to 3, %4 is equal to 0, and 23 to 3, %4 is equal to 0. Since all numbers pass the divisibility check, we can proceed to find the median and calculate the operations. With all numbers passing the divisibility check, the next step is to find the median of the flattened list. For the sorted list, 3, 7, 11, 15, 19, 23, the median is located at the middle index, which is index 3. This means the median is 15. Now, we calculate the total operations needed to align all numbers to the median using steps of size x. The calculation involves summing up the absolute differences between each number and the median, divided by x. Specifically, the operations are abs 3 to 15 //4 plus abs 7 to 15 //4 plus abs 11 to 15 //4 plus abs 15 to 15 //4 plus abs 19 to 15 //4 plus abs 23 to 15 //4. This simplifies to 3 plus 2 plus 1 plus 0 plus 1 plus 2, resulting in a total of 9 operations. Thus, the output for this example is 9. To analyze the time complexity of this problem, we break it into its distinct computational steps. The first step is flattening the 2D grid into a 1D list using the chain.from_iterable function. Since the grid contains m*n elements, this process involves iterating through each of those elements, resulting in a time complexity of m*n. Next, we sort the flattened list. Sorting a list of size k, where k equals m*n, has a time complexity of k*log k, which simplifies to m*n log m*n. After sorting, we check divisibility by x for all elements in the list. This is done in a loop where each iteration involves a constant time modulo operation. With m*n elements in total, this step contributes m*n to the time complexity. Once the grid is processed, we move on to finding the median. Since the list is already sorted, accessing the median is a simple indexing operation, which takes constant time, or O1. After finding the median, we calculate the minimum number of operations required to make all elements equal. This is done using the sum function, which iterates through all m*n elements. For each element, we compute the absolute difference divided by x, a constant time operation. Thus, this final step contributes m*n to the time complexity. When we combine all these steps, the sorting step, m*n log m*n, dominates the overall time complexity. Adding the linear time steps and the constant time median lookup does not change the asymptotic complexity, leaving us with a total time complexity of m*n log m*n. In terms of space complexity, the primary contributor is the storage of the flattened list. This requires storing all m*n elements, resulting in an additional space complexity of m*n. Sorting the list also requires auxiliary space. Python's timsort algorithm, used by the sort function, typically requires k space for a list of size k. Since k equals m*n in this case, sorting adds another m*n to the space complexity. Additionally, we use a few constant space variables, such as the median and the operations counter, which contribute O1 to the space complexity. When we combine these factors, the total space complexity is dominated by the storage of the flattened list, giving us an overall space complexity of m*n. When comparing this optimized approach to a brute force solution, the efficiency becomes clear. A naive method would involve iterating through all possible target values and calculating the operations required for each. With m*n elements in the grid, this would result in a time complexity of open parenthesis m times n close parenthesis squared, a significant computational cost. In contrast, the optimized solution leverages sorting and the median to minimize operations, reducing the time complexity to m*n log m*n. The space complexity remains m*n in both approaches because we need to store the flattened grid. The dominance of sorting in the optimized approach justifies its big O notation, as the linear time steps like flattening and calculating operations do not impact the overall asymptotic complexity. To better understand the performance of this solution, we can analyze best, average, and worst-case scenarios. In the best case, all numbers in the grid are already equal, requiring no operations. Even then, the time complexity remains m*n log m*n due to the sorting step. In the average case, the numbers in the grid differ by multiples of x, and operations are needed to equalize them. The time complexity here remains the same, as sorting still dominates. In the worst case, the numbers are not divisible by x, and the function returns -1 after performing the flattening, sorting, and divisibility checks. This, too, results in a time complexity of O, m n, log, m n. Thus, regardless of the case, the time complexity is consistent due to the sorting step being the most computationally expensive operation. One of the most common mistakes when solving this problem is ignoring the modulo constraint. This happens when we assume that all elements in the grid can be made equal without checking whether the difference between any two elements is divisible by the given value of x. If this condition isn't satisfied, it's mathematically impossible to achieve a uni-value grid. To avoid this, always validate that all numbers in the grid share the same modulo x before you proceed. Another frequent error is not using the median efficiently. Some might mistakenly try to minimize operations by targeting the mean or another central value, but the median is the optimal choice because it minimizes the sum of absolute differences. Sorting the flattened grid and selecting the median ensures the lowest possible number of operations. Lastly, unnecessary complexity in flattening the grid is a pitfall to watch for. Manually writing loops to flatten the grid can lead to harder to read and less efficient code. Instead, use Python's list comprehensions or built-in functions to simplify this process. Another area where mistakes often occur is in handling edge cases. For instance, when all elements in the grid are already equal, no operations are needed. Failing to account for this could lead to incorrect results or even runtime errors in trivial cases. A quick check at the start of your code can immediately return 0 for such situations. Additionally, errors in calculating the number of operations are common. If you forget to divide the total difference by x, you might overestimate or underestimate the required operations. To address this, ensure that you carefully compute the difference between each element and the target value, and then divide by x to determine the exact number of operations. These practices help maintain both correctness and clarity in your solution. This problem is a great example of a pattern that often appears in algorithmic challenges, where the goal is to reduce a set of numbers to a common value. Recognizing that the median minimizes the total cost is a crucial insight. Another key step is validation, checking constraints like the modulo conditions before diving into the main logic. This is not only a part of crafting a correct solution but also something interviewers often evaluate. Efficiency is another important aspect. Sorting the flattened grid has a time complexity of O, n log n, so your overall implementation should avoid unnecessary overhead to stay within acceptable performance limits. If asked about alternative approaches, such as targeting the mean, it's important to explain why the median is superior, especially when it comes to minimizing absolute differences. Finally, thorough testing is essential. Be prepared to handle edge cases, like single-element grids, grids where all elements are already the same, or grids with no valid solution. These steps will ensure your solution is both robust and efficient. This problem shares similarities with other LeetCode challenges. For example, LeetCode 462, which involves minimizing moves to equalize an array, or LeetCode 453, which focuses on equalizing array elements through specific operations. LeetCode 1509, dealing with minimizing the difference between the largest and smallest values in 3 moves, and LeetCode 1886, which tests transformations of a matrix through rotations, are also relevant. Exploring these problems can deepen your understanding of similar concepts. In terms of alternative approaches, brute force is one option. This involves testing every possible target value within the range of the grid, but it's highly inefficient due to repetitive calculations and a high computational cost, often O, n squared, or worse. Another less common approach is dynamic programming, which computes the cost of transforming subsets of the grid. However, this is typically overkill for this problem, as sorting and median-based solutions are both simpler and faster. Finally, binary search is another potential approach to solving this problem. By using binary search, you can attempt to minimize the cost function and identify the optimal value. However, this method introduces added complexity and isn't as straightforward as sorting and directly computing the result using the median. For this specific problem, the median-based approach remains the most efficient and practical choice, given its simplicity and performance. While binary search might be worth exploring in other contexts, here it's generally unnecessary compared to the direct computation approach. Great work! We've covered the key points of problem number 2033, including the algorithm, time and space complexity, and the core insights. Remember, median-based approaches are often a go-to strategy for minimizing differences. Thanks for watching, and don't forget to subscribe for more problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!